Welcome to The Explainer. Today, we're exploring a concept from our sources that honestly sounds a bit like science fiction, but it is rapidly becoming a reality. We're talking about homomorphic encryption. It's often called the absolute holy grail of data privacy. Listen, if you've ever lost sleep over securing sensitive cloud workloads, the insights we're about to unpack here are completely game-changing.
So, here is the fundamental riddle we're solving today. How do you analyze a company's most sensitive data without ever actually seeing it? I mean, it sounds like a magic trick, right? The very nature of utilizing data usually requires us to expose it. We all want to run those powerful machine learning models, complex search queries, and deep analytics. But the second we open that data up to process it, boom, we expose it to hackers, untrusted servers, or just accidental leaks. The real holy grail would be utilizing our data while keeping it completely 100% locked away.
Okay, let's dive into this and break down the difference. Legacy encryption, which is what most of the world runs on today, does a great job securing data in storage and in transit. But to actually compute anything in the cloud, the server has to decrypt it first, and that creates a massive vulnerability gap. Homomorphic encryption is the breakthrough that literally closes this gap. The data remains encrypted during the computation. We are talking zero exposure. The server processes the data while it is entirely locked up.
And this brilliantly illustrates exactly how this works. I really love this analogy from our source material. Imagine you have a locked box full of highly sensitive financial documents. You desperately need a third-party accountant to sort them, but you absolutely cannot give them the key to the box. Now, traditional encryption means you just unlock the box for them, creating all sorts of risk. Homomorphic encryption, though, it's like providing that accountant with specially designed gloves built right into the sides of the box. They stick their hands in, they can manipulate the documents, perform calculations, get the whole job done, all without ever unlocking the box. They never actually see the raw numbers. It's wild.
Let's look at how this actually plays out in a standard cloud computing architecture. It starts with step 1. The client encrypts their private data locally. They are holding the only secret key. Step 2 is where the magic really happens. The client sends that encrypted, totally unreadable data to the server along with a query. The server then uses what's called an eval function to homomorphically compute the query directly on the ciphertext. It computes completely blindfolded. Then, in step 3, the server sends the encrypted result back to the client. Finally, the client uses their secret key to decrypt the result. So the server successfully answered the query without ever knowing what the data was or even what the result was.
Section 1. The 3 levels of encryption, categorizing the tech.
Now, what's really interesting about this slide is how we can break down the operational limits of this technology into 3 distinct phases. First, we have partially homomorphic encryption, or PHE. This is the oldest form, dating way back to systems like RSA. It allows only one type of operation, say only addition or only multiplication, but you can do it an unlimited number of times. Next came somewhat homomorphic encryption, or SWHE. This was a solid step up because it allowed both addition and multiplication. But there was a catch. You could only do them a limited number of times before the mathematical noise in the encryption grew so massive that the data just became unreadable. Finally, the ultimate destination, fully homomorphic encryption, or FHE. This allows unlimited operations, an infinite number of times.
Let's focus on that last one for a second, because fully homomorphic encryption is truly the gold standard of data security. For over 30 years, cryptographers knew PHE and SWHE existed, but FHE, it was just a theoretical dream. That all changed in 2009. A researcher named Craig Gentry achieved the first plausible FHE scheme using what are called ideal lattices in math. Gentry basically figured out a way to refresh the ciphertext mid-computation. It's a process called bootstrapping, which wipes away that mathematical noise we talked about and allows for continuous computations. He literally took this concept from a whiteboard theory into a workable reality.
Section 2. High stakes, revolutionizing cloud and finance. 20 million euros. Under the General Data Protection Regulation, GDPR, that is the kind of massive financial penalty a company can face for a severe data breach. When companies push their sensitive workloads up to the cloud, just a simple misconfiguration or a totally accidental data leak by a cloud provider can trigger these catastrophic fines. The financial stakes of exposing plain text data in the cloud have literally never been higher, which is exactly why this blindfolded computing is moving from research to reality so quickly.
So the crucial point is that homomorphic encryption allows the financial sector to do things that were previously impossible due to privacy laws.
Take collaborative fraud detection, for example. Banks can now pool their encrypted transaction data to identify cross-bank fraud patterns. The AI model can flag anomalies without any bank ever seeing another bank's actual customer data. They can perform secure risk management, outsourcing highly complex portfolio math to cloud providers without exposing their proprietary algorithms. And perhaps most importantly, through decentralized federated learning, they can train incredibly smart AI models across vast data sets while maintaining total data privacy.
Section 3. Trough of Disillusionment, Navigating the Hurdles.
Okay, obviously if it's this perfect, we have to address the elephant in the room. Why isn't this running on my laptop right now? Well, the biggest barrier holding this back is the massive computational overhead. Performing math on encrypted data is significantly slower and way more resource-intensive than processing plain text. Depending on your setup, operations can take substantially longer. Secondly, the implementation is wildly complex. You can't just flip a switch here. You need scarce cryptographic experts to design and tune the parameters so you don't accidentally break the whole system. And finally, the cryptographic keys used in these schemes are often much larger and require highly intricate key management systems just to generate, store, and distribute them securely.
Let's move to and see how this builds toward real practical application. Because fortunately, the industry is aggressively solving these exact bottlenecks. We are officially on the slope of enlightenment. Tech giants are investing heavily in hardware acceleration, creating specialized chips like FPGAs and ASICs built specifically to process this complex math at lightning speed. Researchers are also constantly improving the speed of bootstrapping, that process of refreshing the ciphertext we mentioned earlier. And as high-speed 5G networks become globally available, the latency involved in transferring these larger encrypted datasets to the cloud is being drastically reduced.
Section 4. The Modern Arsenal. HE Toolkits and Implementations.
Because of all these advancements, we're seeing the rise of practical, real-world developer tools. We are finally transitioning out of pure academic research and into applied engineering. If your engineering team wants to start building this tomorrow, these are the top toolkits they're likely going to evaluate. Microsoft Seal is a fantastic C++ baseline. It's widely used, highly reliable, and great for applied teams building their own infrastructure. If you need broader scheme coverage and deep parameter flexibility for some advanced experimentation, OpenFHE is definitely the go-to framework. And if you have a team that wants a more workflow-oriented approach without getting totally bogged down in low-level math, Zama Concrete provides developer-friendly compilation workflows that actually help translate normal code right into FHE circuits.
Think of this metaphorically. It is absolutely time for tech leaders, security engineers, and data scientists to hit update on their legacy privacy architectures. Relying solely on encryption at rest and in transit, it's just no longer enough in an era of massive cloud computing and collaborative data processing. The tools exist today to close that decryption vulnerability gap entirely.
Which brings us to the most important question of all, and one you should definitely take back to your teams today. As AI models inevitably demand more and more sensitive data to train on, will your company be the one that risks exposing it? Or will you be the one that leverages homomorphic encryption to compute it entirely blindfolded? The future of data privacy relies on the latter. Thank you so much for joining me on this explainer. Keep learning, keep asking those big questions, and we'll see you next time.